You know, all around us, there are these vast, invisible networks of tiny sensors, and they're pretty much silently running our world. They're in our farms, our factories, even our hospitals. But what if we can make them way smarter, a whole lot more efficient, and have them last for years on just a single battery? Well, let's dive into how a new, evolution-inspired algorithm is making that a reality.
These things, wireless sensor networks, they're like the unseen nervous system of our modern world. I mean, they're in fields checking on soil, in factories keeping tabs on machines, you name it. But here's the rub. Every single one of those little sensors runs on a tiny battery. And when you have thousands of them, going around to change batteries is, well, it's basically impossible. And that makes energy efficiency the absolute #1 challenge.
So how do you save power? I mean, the obvious answer seems to be just turn some of the sensors off, right? But it is so not that simple. It's actually a fiendishly difficult balancing act.
See, in these really dense networks, you hit a fundamental problem. To make sure you don't miss anything, engineers usually put out way more sensors than are technically needed. This creates what's called redundancy, where you might have multiple sensors all watching the exact same thing. Now, that overlap is great as a safety net, but it's also a massive energy drain if you don't manage it perfectly.
This brings us to 3 goals that are pretty much at war with each other. A great way to think about it is like hiring security guards for a museum. First, you need coverage. You can't have any exhibit left unwatched. Second, you need connectivity. The guards have to be able to talk to each other and to the main office. And third, you want energy efficiency, which in this case means hiring the absolute fewest guards you can get away with to save money. The problem is, if you try to max out any one of those goals, the other 2 almost always suffer.
And this slide shows you the 2 ways you can fail. On the one hand, if you leave too many sensors on, you're just burning through your batteries for no good reason. But on the other hand, if you get too aggressive and turn too many off, you can create blind spots or even break the communication chain, cutting a sensor off from the rest of the network.
For years, researchers have been trying to solve this puzzle with some pretty clever algorithms, and they were good first steps for sure. But they all kind of shared this one fundamental weakness when it came to finding the absolute best solution. And here's that crucial weakness. The older methods were like having just one team of engineers trying to solve the puzzle. They'd find a pretty good solution, but then they'd often just get stuck in a rut. They would converge or settle on a good enough answer because they just didn't have enough different perspectives to see a truly great one. And in this world, good enough still means you're wasting energy.
And this is where a totally new approach comes in. It's called the Redundancy-Aware Island Genetic Algorithm, or RIGA for short. It's a type of genetic algorithm, which means it actually takes its inspiration from natural evolution, survival of the fittest, to find a much, much better solution.
So, instead of having that one team getting stuck, imagine you have 3 separate teams, each working on the puzzle on their own island. Each team is trying to solve it using a slightly different strategy. This island model encourages a much, much wider variety of potential solutions, which keeps the algorithm from ever getting stuck in that rut.
Okay, so what is the secret sauce here? What really makes this thing tick? Well, its power really comes down to 3 key ideas working together in perfect harmony.
First up, there's a process called redundancy criticality mutation. I know it's a mouthful, but just think of it as intelligent pruning. Instead of just randomly turning sensors off, the algorithm analyzes the whole network to figure out which sensors are the most redundant, the ones that have the most backup. It then switches off these low-impact sensors first, saving energy without creating any risk.
Second, it runs a repair phase. This is basically a built-in safety net. After the pruning, the algorithm double-checks everything. It asks, hey, did we accidentally create a blind spot? Is any sensor cut off now? And if it finds a problem, it doesn't just panic and turn everything back on, it strategically reactivates the absolute minimum number of sensors needed to patch that hole, making sure the network is always working at 100%.
And third, it makes those separate teams collaborate, using something called elite migration. Every so often, the best solution, the elite idea from each island gets shared with all the other islands. Now, this is the real game changer. A breakthrough on one island can instantly boost the work on all the others, which dramatically speeds up the search for that perfect energy-saving setup.
So the theory sounds really powerful, right? But does it actually hold up when you test it? Well, the results, they pretty much speak for themselves.
Yeah, the results are incredibly clear. On this chart, a lower bar is better. That's it. A lower bar means fewer sensors are active, and that means more energy is being saved. And you can see, compared to the older methods, this new RIG algorithm consistently finds a solution that needs way fewer active sensors to do the exact same job.
So just how much better is it?
Get this, we're talking about a reduction of around 25 to 30% in the number of active sensors needed. That's not just some small incremental improvement, that is a massive leap in efficiency.
And that 25 to 30% reduction, what it really means is that the batteries drain much more slowly. You can see it here, the energy consumption line for our IEGA is so much flatter. This means the entire network can stay up and running for a significantly longer time before the first battery even thinks about dying.
So, why does all this technical stuff matter to you? Well, it means our future tech can be way more reliable and sustainable. I mean, think about smart cities, where traffic and environmental sensors don't need their batteries changed for years. Or think about precision agriculture, where soil sensors can last an entire growing season, maybe even longer. It all adds up to less energy waste and less need for that expensive, difficult maintenance.
Really, the powerful takeaway is just this. By making our scheduling algorithms smarter, we can dramatically extend the life and the reliability of these sensor networks that our world is really starting to depend on.
And it leaves you with a final thought, doesn't it? As we keep weaving technology deeper and deeper into the fabric of our lives, maybe the biggest innovations won't be in the hardware that we can see and touch, but in the intelligent algorithms working behind the scenes that make it all run efficiently and sustainably. Thanks for joining this explainer.